The neutrino oscillations argue that the neutrino has a mass unlike the standard model, so it requires the extensions of the standard model. In the standard model, there's a left-handed neutrinos, but there's no right-handed neutrino because the right-handed neutrino is the gauge singular and no hypercharges. But to explain the massive neutrino, we need the left-handed and the right-handed neutrino both. But if we consider only the Dirac mass term, which is generated by the Yukawa coupling term, then the Babs scale of the Higgs is around 100 GeV, and the other baramion, like as a cork or charged lepton, has a similar scale like as the MEB to the GeV scale, but the Yukawa coupling for the neutrino should be the small to explain the small neutrino mass, because the neutrino mass bound is roughly the sub-electron volt. The upper bounds comes from the CMB or treated by the decay spectrum, and the lower bounds comes from the neutrino oscillations in the triple regime. So to explain such a small scale of the neutrino mass, naturally, we usually adopt the additional Manara mass term. And if the Manara mass term is larger than Dirac mass term, this is called the Seesaw limit, which keeps the small neutrino mass naturally. In the matrix form, this can be written by the MD times the inverse of the Manara mass matrix times Dirac mass matrix. The typical scale is given by for the order ones of the Yukawa coupling strengths. The Manara mass term scale is 10 to the 9 to the 10 to the 15 GeV to explain the sub-electron volt small neutrino mass scale. And today I want to talk about the sub-neutrino mass model beyond the Seesaw, the canonical, just a simple Seesaw relation. First of all, in the single flavored case, the eigenvalues are given by just m square plus m, and the active star neutrino mixing, the sign scale theta is extremely small, so that this can be approximated as just a theta scale. And this mixing angle is given by the ratio between the Dirac mass and the Manara mass term, and also we can realize this as a matrix form. And because the mass eigenstate can be written by the linear combination of the left-handed and right-handed state. And because the active neutrino mass eigenstate has the mixing component with the right-handed neutrino spinor, so the such active solar neutrino mixing angle gives a non-unitarity term. So the such a determinant of the neutrino mixing term is still 1 for the small active solar neutrino mixing angle, but the left-handed components in the active neutrino mass eigenstate has a non-unitarity component as a 1/2 theta daggers. Now I turn to the extensions of the system mechanism to explain the neutrino oscillation data. The minimal Seesaw required that at least 2 right-handed neutrino. We can parameterize the Yukawa matrix by using the Casas-Ibarra's notation. Here is the V is the valve of the Higgs, and the U is the PMNS matrix. mu is the active neutrino mass matrix. Capital M is the heavy solar neutrino mass matrix, and R is the complex orthogonal matrix. And in the 2 right-handed neutrino, so it's a minimal system model. The size of the capital M is the 2 times 2, so the orthogonal complex matrix should be the derivative size of the matrix. But usually, also we can adopt the canonical Seesaw relations with the 3 right-handed neutrino. Like there are 3 generations of the active neutrino, and correspondingly we can also adopt the 3 habit solar neutrinos, so there are mixing between the generations, and also the mixing between the star neutrinos component. Also, beyond the Seesaw relation, there's also other extensions in the habitual neutrino block. The first one is inverse Seesaw. We can introduce the additional extra singular, so-called S, new fermion. In the inverse Seesaw mechanism, there is the monomer term of the extra singular, but there's a no monomer term for the original right-hand neutrino capital R. Instead of that, there is a mixing term between the RHN and extra singular. So the monomer term capital M times N times S. In this case, the active neutrino mass m nu is given by the following form: mu times m squared over m squared. Here's the mu is a small scale rather than the monomer mass term. So the such a small mu, the low scales of the mu term is the testable in the collider search. And in the heavy neutrinos block, this second and the third law and the Coulomb block. This is a form of the Schroeder-Dirac form because the mu is extremely smaller than the capital R. So the two heavy neutrinos tight forms the Schroeder-Dirac pair with the small splittings by the mu terms. In this case, the two heavy neutrinos are Schroeder-Dirac pair, so the Lambda number violation process is a surplus, like a neutrino cluster over the decay through same sign dilepton signal. Because in the light of the neutrino cluster over the decay, the two heavy neutrinos once the cancel each other out. This light is proportional to the Lambda number by lighting terms of master mu. So the if the mu term is smaller than capital M, then the LMV process is a surplus. But still, the Lambda flavor violation process, the heavy neutrino loop corrections and the non-unitarities of the PMLS matrix in the active mixed matrix is still sizable, so this is testable. Also, the small scale of the mu is a kite collider testable. The other possible ones are linear Seesaw ones. Instead of the mu terms of the mu SS term, we can also give the mixing between the active neutrino nu and the extra singular S. Then the active neutrino mass eigenvalue is given by the ml times md through the m. So now the active neutrino is linearly proportional to the Dirac mass term, so it is called the linear Seesaw. The different one is the such ml terms are generated from the Higgs bulb. In the inverse Seesaw model, the mu terms are not generated from the Higgs bulb. It is just given by the monomer mass terms of the S. The other possible one is a double Seesaw. Still, there is a mu terms for the extra singular, but the mu is larger than the monomer mass m now. Then there is a double Seesaw relation. The active neutrino mass is given by the same ones, and this there is additional Seesaw block, so that this there is the monomer mass term. I mean the mass eigenvalue has also the Seesaw relations. M squares of the mu. Under such hierarchies, there used to be large mu's and the intermediate scales of the capital M and the small Dirac mass term. And also we can give some symmetry, non-abelian symmetries for the extra fermion. In the type 1 Seesaw, the right-hand neutrinos is the singular fermions. And we can write the dimension 5 Reinberg's properties. If the happy minor neutrinos are integrated out, then the dimension 5 properties given by the LLHs, H's through the amount. But in the type 2 and the type 3 Seesaw, now the additional scalars and the fermions, the charges are under the SU2 symmetry. In the type 2 Seesaw, the capital delta is SU2 triple scalar. So there's charges around the SU2 symmetry. And if we integrate out the scalar particle capital delta, then the higher dimensional property is given by the similar form. But now there's a linear coupling between the two Higgs and the triple scalar with the mass dimensional coupling. So the in the type 2 Seesaw, now the active neutrino mass eigenvalues are proportional to the couplings linearly because there is a massive mutuums in here. In the type 3 Seesaw, now the fermion is charges around SC2 in the triplet form. So this capital sigma contains the neutral components around the charges the one, and the active neutrino mass eigenvalues are similar form to the type 1. Such a type 1, 2, and 3 Seesaw can be tested in the phenomenological point of view. First of all, like the neutrino last over the case, or the same sign dilepton signal, such as lepton number variation process is expected. And for the active stellar neutrino mixing corrections, the original permanent active neutrino mixing matrix has a non-unitarity. And some specific quantities in the electroweak theory has the correction by the mass terms and active stellar neutrino mixing is called the electron-weak precision test. And the heavy neutrino loop gives the correction to the branching radius of the lepton fiber variations like the muon go to the electrons and the protons process. And the other possible phenomenological task is the cosmological point of view. The leptogenesis, the case of the heavy neutrinos, can generate the leptonous material and explain the valence materials of the universe. And the heavy neutrinos, the loop can correct the Higgs mass, so that this can resolve the natural neutral hierarchy problem. There is a Manor mass term as a correct is the Higgs mass with Yucca couplings in here. And also there are direct collider such if the heavy neutrinos mass scale at a T scale, the proton-proton collisions produce the heavy neutrinos which is proportional to the mixing angle, and it decays and gives some specific signal. So depending on the heavy stellar neutrino scale, there are several regimes. Here the Seesaw relation. First of all, if the Manor mass is smaller than the subelectron bolt, this is called the Schütte-Dirac. To explain the subelectron bolt mass scale of the active neutrino, the Schütte-Dirac should be the still 0.1 electron volt. So the Dirac mass term should be the still 0.1 electron volt. So the Manor mass term is smaller than the Dirac mass term. So this is called the Schütte-Dirac limit. And if the Manor mass term, the stellar neutrino is electron volt scale, this is a 3 plus 1 regime. This is also proposed to explain the many neutrinos anomaly, like as the reactor anomaly or gallium anomaly or the mini-Bragg excess one. And the kilo electron volt scales of the stellar neutrinos can explain the and also can become the candidates of the warm dark matters. And the TeV scales of the heavy neutrinos requires that the 10 to the minus 4 GeV scale of the Dirac mass term. This is quite collider tassible. And the 10 to 9 to the 10 to the 15 GeV, this is GT scale, Gauss scale, or the baryogenesis in the cosmological approach. Now the Dirac mass term is the scale of the electroweak scale to 1 GeV in here, but this is not collider testable. In the remaining time, I will turn to the some other possible approaches of the neutrino mass model. This is the radiative neutrino mass. Instead of the Seesaw relation, we can make the three-level Manor mass term is forbidden by some specific symmetry. Instead of that, the active neutrino mass, the smallness of the active neutrino mass, comes from the loop effect. In the loop level, there is the 1 over the 16 pi square factors, and there are heavy Manor neutrinos in the denominators for the loop propagators. And the symmetry breaking coupling is very small, such a 3 characteristic gives a small neutrino mass in the loop level. Luckily, the small neutrino mass has the following form: loop factors, small Lucas coupling, and as a loop functions, it contains the heavy Manor neutrino mass and some specific mediators. There are several radiative neutrino mass models, and this can be classified topologically through the loop level. The minimal radiative neutrino mass model, the Z model, this is the one loop. Here's there's additional Higgs double laws that are introduced, the capital Pi, and there are the two linear coupling between the original Higgs and the charged singlet. So this is the corresponding loop diagram. This is the Lapton double law which contains the neutrino, and there is a two linear coupling, charged Higgs, standard model Higgs, and additional Higgs double law. And from the Borstum, there is the Lapton double law electron, right-handed electron single law, and the standard model Higgs or the additional Higgs double law coupling. Such a G model is the minimal one, and also we can extend this to the G Barber model in the two loop level. Here the stable charged singlet in here, and there are the doubly charged singlet, small h's plus plus. There's a two loop. Okay, maybe I think this is K. So that there are two linear coupling between the charged singlet, and doubly charged singlet, and they are the same term, the standard model Higgs, Lapton double law, and the right-handed electron singlet. So that these couplings occur, and the two loop generate the active neutrino mass. And the dual loop case is a K and T model. There's a two singlet S1 and S2, and the right-handed neutrinos, and the S1 scales, there is two scales coupling, cortex color coupling in here. So this is a dual loop 1 to 3. The other possible one is Scott-Jardine model. There is the S2 inert double law test, and this is linked to the stable dark matter. There is Eta scales and the Hubble scales, the cortex coupling, and the S2 double law. Eta is S2 double law. And all particles, all of the terms that are forbidden by imposing the Z2 symmetry, so the two level manner mass term is impossible in here. And the other one is the Laptop-Kirk model. This is a one loop example of the Laptop-Kirk model. The scalar S and also the scalar R is charges under the S3 and S2 simultaneously. This gives the following form. Here is also the linear coupling between the three different scalar, and here's the S and R changes from the lepton to the quark. Also, the supersymmetries with the R parity violation can provide the radiative neutrino mass. There is a bilinear one and the two linear term. For the bilinear term, there is the neutrinos and the neutralino mixing term. The neutralino comes from the neutral gauge term. So there is the neutrino mixed term from the neutrino nu to the N tilde, and N tilde has a fermion and the fermion loop, so this gives the neutrino mass in the radiatively. So today we discussed many models of the neutrino mass to explain its smallness. From the Seesaw mechanism, and we extended the canonical and minimal Seesaw, and the other extended cell neutrino blocks like as inverse double linear Seesaw, and we turn to the some of the symmetries to the right-handed neutrinos. Type 1, 2, 3 Seesaw, and there are the many phenomenological tasks of the Seesaw mechanism, like as RFV, RMV is the non-unitarities of the PMNS matrix, and electroweak precision tasks, and the leptogenesis, and the collider tasks, table scales of the TB, and the natural list of the Higgs mass. And depending on the neutrino mass scale, there are several regimes, like the pseudo-Dirac pairs, or 3 plus 1 regime for the neutrino anomalies, and the killer electron bolts, both one documented candidate and TB scales, the collider task table ones, and the G2 and the baryogenesis with the electroweak scales of the Dirac master. And finally, I talk about the radiative neutrino mass with the loop effect. There are several models from the one loop to the two loop, or the links to the document, so the Laptop-Kirk, or the supersymmetry with the R parity violations.